Hello everyone. Have you ever wondered how those tiny, powerful analog circuits hidden inside almost every electronic device are actually designed? Well, it's not easy. Designing analog circuits takes expertise, lot of trial and error, and ton of time. But what if AI could help us automate this process? That's exactly what we set out to explore. We, Team Outlaws, and today I'm super excited to introduce you to cktFormer, our transform-based approach to analog circuit design. Manual circuit design isn't just time-consuming; it is prone to errors that can lead to costly redesign cycles. While AI has optimized many parts of manufacturing, analog circuit design remains a significant bottleneck. Our goal with cktFormer is to bridge this gap, using advanced AI to make circuit generation faster, more accurate, and more efficient. So, what's been tried so far? Well, sequential models like analog coder treat circuits like language. Great idea, but circuits are linear, so they struggle. Graph neural networks, like circuit GNN, get the graph structure, but they are limited by how much they told in advance. And reinforcement learning like models, like AutoCircuit, are powerful but need a crazy amount of simulation to learn anything useful. All of these approaches have their strengths, but they often miss the bigger picture literally. They are good at making valid circuits, but not always the best ones.
This is where cktFormer comes in. We leverage the power of transformer models for their ability to capture complex relationships in data through the attention mechanism. Instead of one model, we use two interlinked transformers, one predict the next component like resistor or transistor to add essentially the node of our circuit graph, the other one to predict the connections between these components, the edges of our graph. We explore both cyclic version and non-cyclic version for this edge prediction model. Let's look at how we represent circuits in a machine understandable format for this task. There are two main parts to this: component encoding and graph encoding. Starting with component encoding, each type of component like resistor, transistor, or voltage source is assigned a unique identifier. Individual components pins are modeled as separate nodes. For complex components like transistors, we break them down further, representing their terminals, collector, base, and emitter. These components are then stored as an embedding in a lookup table. Now on to graph encoding. We use an adjacency matrix to represent the connection between components. Here each row and column represent to a specific component pin. A 1 in matrix indicates a connection while a 0 means no connection. This representation only captures the connectivity but also makes it easier to add or modify components during generation. The diagram shows an example circuit on the left with its graph representation on the right. Node and edge data are embedded and fed into the model. This graph-based structure allows the model to grasp the circuit data. Next, let's work through the model architecture used in our approach. This design is composed of two main parts: the node prediction model and the edge prediction model. We begin by feeding in two types of inputs: component sequence and the circuit geometry in the form of an adjacency matrix. Both of these are encoded separately. The node prediction model processes the current graph structure using an encoder. The decoder then predicts the next component to be added. This prediction is mapped to our component vocabulary, resistors, capacitors, transistors, etc. This allows the model to incrementally grow the circuit from an existing partial design. Next comes the edge prediction model, which decides how the newly predicted components connects to the rest of the circuit. This can be done in two ways. Non-cyclic, where all connections are predicted in a single forward pass, or cyclic, which adds connections incrementally. The edge prediction uses graph attention mechanism enhanced with an edge bias to accurately identify which components should be connected. Finally, we have a refinement step that polishes the output before decoding it back into the updated component list, and the new adjacency matrix represents the circuit geometry. This combined architecture allows the model to design circuit in an structured and modular way.
So, how well does it work? Actually, pretty great. We tested it using the analog Gini benchmark dataset. Our base model, which combines node prediction model with non-cyclic edge prediction model, reached almost 90% circuit validity. That beats the previous best of analog Gini of 73.5%. Our edge prediction model alone had over 96% accuracy. We have also found something interesting. The model needs around 10 components in the sequence to start making meaningful predictions. Just like a human designer, it needs some context before it can recognize patterns, like filters or amplifiers. Because of this, we have evaluated our combined model using node sequences of length 10 by passing them through the first to the node prediction model and then through the prediction model. The real innovation of cktFormer is in how it uses transform attention to capture the global structure of circuits, not just locus patterns. That makes it great for both creating full designs and completing partial ones. So, what's next? We want to train on real world circuit designs that use component libraries from tools like KiCad and LTM Design. We want to predict actual component values like resistance or capacitance. Maybe even add graph neural networks into the mix for deeper insights. And eventually build real-time design suggestions like autocomplete but for circuits. In short, Circuit Former shows how AI can help us rethink and look circuit design from slow and error prone to fast and innovative. Thank you for watching. And a big shout out to our amazing mentor Dr. Tharidu Bandaragoda for his constant support and guidance.